So assalamu alaikum everybody and welcome to another Al-Mawrid Institute Canada lecture presenting Dr. Mir Faizal for a third lecture in a series on the topic of God, reality and science. Dr. Faizal is the director of the Canadian Quantum Research Centre and has affiliations with the University of Lethbridge and the University of British Columbia, Okanagan. He has over 150 publications in his field where his focus has primarily been on theories of quantum gravity. Dr. Faizal, being a devout Muslim, has also spent considerable time and effort reflecting on matters of faith and his scientific understanding of the world. And he will be sharing this understanding with us. Today's lecture will be focusing on the topic of understanding God and the limitations of language. Please go ahead, Dr. Faizal.
So we discussed in the first lecture how we fix the meaning of God to mean the most fundamental aspect of reality. But then we saw that any description of this most fundamental aspect of reality can, in language, is at most an approximation, because human languages evolved to discuss objects at our scale. And it's not even possible to discuss objects at a slightly different scale from our scale consistently using our language. But then the problem with this thing is that any approximation breaks down beyond the level of validity, beyond its level of validity. So if you have an approximation, it is only valid till you can only describe a system using that approximation till the level of validity of that approximation. For example, take general theory of relativity, which describes the geometry of space and time. But because singularities develop at the center of black holes and at Big Bang, the space-time description of reality breaks down at that scale, and general relativity can no longer be used to describe physics at that scale. Similarly, even if you go to a slightly different scale, slightly smaller scale than our scale, you go to quantum scale, you can have, at our scale, things cannot be present and absent in the same state at the same time. Whereas in quantum scale, it is a possibility that particles can be present and absent at the same time. And so you can see that the classical description of such states would become impossible in our language. So you can see that language is only suitable to describe phenomena for which it has been evolved, and then our language can only describe phenomena at our scale. So when we're discussing something like fundamental aspect of reality, you have to understand the limitations of language there. At most, what you're doing is you're describing an approximation, which of course, because the approximation breaks down, is supposed to break down. So the first two papers are about Hawking and Penrose's paper about how so these two first papers are about singularities and how singularities are something inbuilt into general theory of relativity. They're not a mathematical artifact, and how general theory of relativity cannot describe space-time, cannot describe reality at that scale, because the space-time description of reality does not hold at that scale. The remaining papers after the first two papers are papers about construction of quantum states where a particle is present and absent from the same state at the same time. So you have particle being present in a state plus particle being absent in a state, and this together forms a quantum state. And construction of such states. But then you see one of the ways to resolve this is to have a better approximation. So for example, general relativity develops singularities, but it is expected when you construct a new theory of quantum gravity using a new language, it might not be a space-time description of reality, but it will be a description of reality in that new language, and you would not have these inconsistencies, you would not have these problems with singularities at that scale. Similarly, when due to the language of quantum mechanics, you can use the concept of quantum superimposition and explain this state of particles being present and absent from the same state at the same time, due to this new mathematical quantum fuzzy language. Then you can see that our classical language is the language describing our classical physics was only an approximation to this more fuzzy language. And in this more fuzzy language, these states can be properly understood. And then we come to this question: if this holds true at slightly different scales, can we if not have a perfect, but at least a better approximation to the most fundamental aspect of reality in a new language. I'm not saying this would be the perfect language. Fundamental aspect of reality cannot be explained in language, but would it be a better language? A better language which would be better than the deterministic language that we are using. So again, so these first few papers are papers where you have used a specific approach to quantum gravity to remove Big Bang singularity, and as I told you, we don't even have a consistent theory of gravity. We have approaches to quantum gravity, and even with those approaches, and or just by inputting quantum information in, the fact that space-time becomes quantum mechanical, you can remove singularities. In fact, this paper in 2018, we actually showed that if you input quantum effects in general relativity, the results of Hawking, the seminar results of Hawking and Penrose don't hold, because quantum effects prevent the occurrence of such singularities. And then the remaining papers at the remaining last few papers are papers about how in quantum mechanics you construct a new language in which the state of particles being present and absent at the same time from in a particular state is actualized, and it doesn't create any conceptual problems from the perspective of quantum language. So now let's look at quantum mechanics in some detail and see if we can motivate the results that we know from quantum mechanics and develop a new language motivated by those results, and if we can address some of the problems that would occur from a deterministic language when describing the most fundamental aspect of reality using this new language, new fuzzy language that would be motivated from quantum mechanics. You see, quantum mechanics definitely uses a new mathematical language, and in that mathematical language, position and momentum cannot be measured together. But I want to stress this point: it's not just they cannot be technologically measured. The statement is more deeper than that. The statement basically states that if you measure position, then it's not that momentum can't be measured. It becomes meaningless to talk about the measurement of momentum. You just can't even talk about it. It becomes a meaningless statement. You see, let's break this down in a more proper way. I can have two statements. Statement one could be a particle exists at a certain distance from a fixed point. The statement two could be that this particle has a certain momentum. Now, classically, these statements might be true or false. The particle may exist here or may not exist here. The particle may have that value of momentum or may not have that certain value of momentum. But whether it's true or false, both these questions are well defined, and you can answer both of them as true or false. That's fine. But quantum mechanically, if you answer the first question and find that particle does exist at a certain point from a certain fixed distance, the second question becomes meaningless. Now, it's not that the second question is false. The second question, you can't even answer that. It becomes meaningless to talk about the second question. So this is a very important difference. You see, you can say that, for example, particle one is present at a certain distance, say 5 units from a fixed distance, and it has a momentum, say, of 6 units. Now if you answer yes for the first question, yes, the particle one is present at a distance of, say, 5 units from a fixed distance, it's not that the second answer becomes wrong. The second statement becomes meaningless. You can't even talk about it, and that is because there is a deeper thing here. There's a restriction on the amount of information you can take out of this mathematical system, and this idea of restricting information, relating quantum uncertainty to information theory, has been very well studied. So, for example, the first few papers I have highlighted here are about quantum mechanics and quantum uncertainty, and this is a book. These are some nice lectures of Weinberg on quantum mechanics if anyone wants to read it. But the last few papers are about how quantum uncertainty is actually an information theoretical construct. It is constructed in the language of information theory, and it's very rigorously constructed in the language of information theory. And in the last papers, that is what is being discussed: how this quantum uncertainty is actually an information theoretical restriction on the amount of information that you can extract from this system. Again, I want to highlight one thing, that uncertainty principle is a very general principle. it even holds for quantities like spin of a point particle, which has no classical analog. There is not in classically there's nothing like a spin of a point particle, but quantum mechanically you have an intrinsic spin associated with fundamental particles, which at least from the perspective of particle physics are point-like particles. And so quantum mechanically you can have things which are very abstract, and you can still have quantum uncertainty, the uncertainty principle that these quantities obey. In fact, in the first lecture, we talked of fields as abstract mathematical objects which are expanded in flat space-time and which give rise to particles. Even fields have their own uncertainty, and by a slight modification of that uncertainty, you can actually get rid of singularities. And singularities, that's a very interesting result. If you modify the uncertainties at the level of second quantization, you can actually get rid of singularities. And you can even do this at the level of third quantization. The uncertainty even holds at the level of third quantization. And this has nice consequences for the multiverse. So you can see that the uncertainty principle is a very general principle in quantum mechanics. It should not be thought in a restrictive sense, only applying to momentum and position of a particle. And it should be thought as a very general statement made about the mathematical structure of quantum mechanics, and comes fundamentally from information theoretical restrictions on the amount of information you can extract from this system. So in a very general sense, you can have two statements again. The quantum mechanical system obeys property 1, a quantum mechanical system obeys property 2. And classically, both these systems can be true or false. But quantum mechanically, if you answer the first statement, the second becomes meaningless, because again, you have an information theoretical restriction on this system. Now, what these property 1 and 2 are depends on the system you're analyzing, the property you are analyzing, and can be something even very, very abstract. So here I thought I'll cite some papers. First few papers are about quantum spin and how quantum modifying the uncertainty principle, and that modify for the spin of quantum mechanics. And this modification, especially in this 2017 paper, was actually something interesting. It was done motivated by quantum gravity. Then you have my paper and another paper in 2020 where you modified the second quantization to get rid of the singularities. Then in the last two papers, you studied the uncertainty at the level of third quantization with consequences for multiverse. So you can, again, I just wanted to highlight the fact that uncertainty principle is a very, very broad principle, and it fundamentally comes from information theoretical restrictions on the mathematical structure describing quantum mechanics or quantum theory in general. Okay, now there are limitations. You can have such limitations on when you have such limitations on mathematical structure describing quantum mechanics, you can have such limitations on other logical structures. And language being a logical structure, which of course evolved at our evolution due to evolution at our scale to explain objects around us. But at the end of the day, language is a logical structure. So you can have such restrictions on language. Now, motivated by quantum mechanics, you can place such restrictions on linguistic structures and see what kind of fuzzy language you develop and what would be the consequences of such a language. I want to point out one thing here. I want to just clarify one thing, that this is not you see, quantum mechanics works in a specific mathematical setting. Even though there has been some work done in applying similar settings to language, this is not needed for my present discussion. All I need is to make this fundamental observation that quantum mechanics fundamentally comes from an information theoretical restriction on a mathematical or logical system, and language being a logical system, we can impose this restriction on it and this would produce a new fuzzy language with an intrinsic limitation on the amount of information that can be extracted from it. And in this new fuzzy languages, some paradoxes which would occur from deterministic language would go away. So this is all I would need. So I thought I will share some work here. Again, these are certain papers where actually people have discussed the relevance of quantum mechanics in linguistics has been discussed. This is again a active field of research where quantum mechanical structures are their implications in language has been discussed. So this is very interesting. The last paper, especially quantum physics and linguistics, a composite diagrammatic course. This is a really interesting book if anyone wants to actually read this. But let's approach let's try to see if we can impose some similar restrictions on language. Having done that, what kind of implications we will have? So we will again have these two properties, property 1, property 2, and if you answer affirmatively about property 1, you can any discussion about property 2 would become meaningless. So for example, property 1 could be free will exists, and property 2 could be predetermination. There is predeterminism. Now, if in any argument you're using free will, any discussion about predestination, about fixed future becomes meaningless, and vice versa. If you have a discussion about fixed future, any discussion about free will becomes meaningless. But you can see that because of the restriction of this information theoretical restriction on language, if you answer affirmatively about property 1, yes, free will exists, then it's not that the second thing is false. The second discussion about the second property about predestination becomes meaningless. It becomes meaningless now to talk about predestination. And the same thing, if you're talking about predestination, then it becomes as a second property, then it becomes meaningless to talk about free will, because you have to, at the end of the day, you have to see what you're really doing. What you're really doing is you're extracting information about the most fundamental aspect of reality using language. But since the most fundamental aspect of reality is anyway beyond language, all you're doing is you're approximating. And because of this limitation of approximation, language, this struggle, there's no reason why you would be able to extract infinite amount of information. There should be some information theoretical restriction on it. In fact, since information theoretical restriction even holds true for physical systems at slightly different scale from ours, it should certainly hold true for the most fundamental aspect of reality. You can deal with problem of evil in the same way. Property 1 could be God is all powerful. Property 2 could be God is good. So if you have answered property 1, you do not need to answer property. Like any discussion now about property 2 would become meaningless, and vice versa. There's this famous paradox people bring out in language. Can God create a stone that God cannot lift? Easily now answerable in this fuzzy language. Property 1 could be God can create any stone. Property 2 could be God can lift any stone. Now, if you have answered affirmatively about property 1, yes, God can create any stone. Now any discussion regarding property 2 would become meaningless. So you can see that there are problems that come because of the deterministic nature of language trying to explain something which is beyond its level of validity. And by slightly modifying the language and putting some intrinsic fuzziness, all those paradoxes actually go away. But there's something really important. Even though the old paradoxes have gone away, the fundamental aspect of reality cannot be comprehended in language, because no matter what language you're using, it's still motivated by reality at a certain scale, and fundamental aspect of reality is the most fundamental aspect, is so fundamental that you can't describe it in language. So even though we have removed these old paradoxes that could have occurred in a deterministic language, and I can't think of any paradox that would occur in this fuzzy language, but I would expect, because even this fuzzy language is at the end of the day only an approximation, you might even get new paradoxes. But then you can develop a more abstract language and get rid of those paradoxes also. You can in that new abstract language, these paradoxes will not occur. But the main take I want to stress here is that we have to differentiate between two things. But between one is God as the most fundamental aspect of reality, and another is the linguistic approximation used to define God or describe God. Any linguistic approximation used to describe God is at most an approximation, and since God cannot be described in language, any language will fail at a certain scale. So these failures should be attributed to the limitation of language, which you can again see by just modifying the linguistic structures slightly. Many of the old paradoxes go away, and I would expect new paradoxes to come up. But then this is what would be expected, because these are the limitations of language in describing something which cannot be described. God cannot be God cannot be described in language, and so I would expect these paradoxes to occur. And yeah, that is the main point I wanted to make here.